Hey guys, we're going to be working on the sine rule today. So what I've started off with is that triangle that we've spoken about previously. Any triangle can be represented as your three angles, capital letters A, B, and C, and then the opposite sides in lowercase, little a, little b, little c, opposite those angles. Now, with the sine rule, you can express it in two different ways. One where the signs are on the bottom, the other ones where the signs are on the top. And simply as the ratio of the side and the sine of its opposite angle, so A and the opposite angle, capital A, is equivalent for each of those sides and their opposite angles. So A on sine A is equal to B on sine B is equal to C on sine C. And those ratios are the same. And if we flip each of those fractions or ratios, then we get that's still the same thing, are all equivalent to one another. And depending which way is where our unknown, what we're trying to find is, then we'll use one, and for other situations we'll use the other. We'll go through some examples and hopefully that will make a bit more sense later on. Now, where this comes from, and I haven't done a complete proof, that might take a little bit of time and it's probably not all that worthwhile to us at this stage. There's other videos, I'll try and link one, see how that goes. So, real quickly, for an incomplete proof, we've got the triangle that we've been using, A, B, and C, okay? And we are going to express the height in two different ways. Sine B is equal to opposite A. I've messed up. This is supposed to be H opposite on hypotenuse. That's better now. H on A. We multiply both sides by A. We get the height is equal to A sine B. On the other side, we're doing this from the angle A, so sine A is its opposite, still the height, on its hypotenuse, B over here. So, again, height is equal to B sine A. Now, these are both expressions of the height, so they are equal to one another. A sine B is equal to B sine A. And they are both equal to H if you wanted to have that on the side there. Rearrange this equation here, divide this on both sides by sine A and by sine B, and you'll get one small part of our sine rule. Now, for the complete proof, you would need to repeat for the various angles and heights and show that they're all equal. But you would also need to do that for the obtuse case where your angle or one of your angles is greater than your 90 degrees. And that takes a little bit of time. So let's just move on to some examples instead. Example 1, we've got evaluate x correct to 1 decimal place. So with the sine rule, we are looking for sides and their opposite angles. So we need a relationship between this side and its opposite angle. Okay, we don't know that yet, so that's kind of a problem at the moment. But we do know two angles within this triangle, and hopefully we know that the angles within a triangle add up to 180 degrees. So we know that this angle here, let's call that theta. Theta is equal to what's left over if we take 73 and 39 from the angles in a triangle. And just to make sure I don't mess that up, 180 take 73 take 39, 68 degrees. So The reason we're doing that is because it's opposite the unknown side which we're trying to work out. And opposite sides and opposite angles, we know one side and we know its opposite angle here. So we've got a relationship between x and sine of 68 and 8 and sine 73, because that side and that angle are opposite one another. The unknown side x and 68 are opposite one another. So keep that in mind when you're doing your sine rule. The reason that I have decided to use the length up top is because my unknown x is a length, and keeping that up top just means that I can multiply both sides by sine 68. 8 times by sine 68 on sine 73. And it just makes it a lot easier to rearrange, so we'll stick to that. 8 times by sine of 68 divided by sine of 73. Again, it's approximated here, 2, and we only need to go to correct to one decimal place, so 7.8 back to the book, 7.8 centimeters. Alright, so opposite sides and angles. Once you've got a couple pairs and only one unknown, yeah, it's going to help us to get to our answer. We'll do something slightly different, for example, 3. Now, when you're trying to find the angle for sine, you have two possible solutions. It doesn't necessarily mean that there are always two solutions, but that because sine theta and sine of 180 take theta are the same value, you might need to go back to your unit circle to try and remember that. So if you're trying to get your angle and you're doing the inverse of sine, there is actually two cases. One where you have the angle that you get from your calculator, and then 180 take that angle is another possible value. And let's see that in action for example 2. Okay, we've got an angle theta, which is what we're trying to work out to the nearest degree. We have its opposite side. Okay, and we have 81 degrees and its opposite side. Now, because theta is the angle being unknown, I'm going to use sines on top for this part. Okay, so sine theta on 6.5 is equal to sine of 81 on 8.4. Now, quickly rearrange, so it's been divided by 6.5, so I multiply by 6.5. Sine theta is equal to 6.5 times by sine 81 on 8.4. And now I need to take the inverse, so theta is equal to sine to the negative 1 of everything that was on this other side, 6.5 sine 81 on 8.4. And when we go to our calculator, we'll go sine to the negative 1 of 6.5 times by sine 81 divided by 8.4, and we get theta is equal to 49.8 degrees. But we want to check the obtuse case as well. So looks like this. We've got our angle. The other angle that is possible is 180 take the answer that you got, which is 100 and I'm going to mess it up, aren't I? Go back to the calculator just in case. 180 take 1.8. There you go. 130.2 degrees. And the question itself is asked us to go to the nearest degree, so it'd be 50 and 130. But what we want to check is, does the obtuse case actually work? We already knew that one of the angles is 81, and we get a problem if we were to try that. Angles in a triangle have to equal 180, but if one of our angles was 130, and we've even rounded down in this case, then it is greater than 180, which means only theta equal to 50 degrees can work. Okay. Check the obtuse, make sure you're aware that it is a possible solution, but check if it actually works within the realms of the information that we've been given to begin with. Let's try one more example. A little bit trickier, and we're going to have a bit of carry through in this one. We've got Jermaine sees that the top of a sand dune at the end of a beach, is at an angle of elevation of 16 degrees. On walking 40 meters closer, she finds that the angle of elevation increases to 22 degrees. So we're going to have this angle here, angle of elevation from Jermaine to begin with is 16 degrees. But Jermaine walks 40 meters closer to the sand dune. So once she finishes our 40 meter walk, the angle of elevation to the top of the sand dune is 22 degrees. And the sand dune, we can assume, is at 90 degrees to what? Oh, to the ground. Now, we need to find the height over here, and it's seemingly like we don't have enough information. Okay. It might be useful to get a few more angles to understand where we can use the sine rule. I know that if we were to find the hypotenuse of this right angle triangle, or this line that divides what you might see as two triangles, it can help us to get the height. I'm just wondering if the hypotenuse, if we could find that, whether we could use that to find the height. Yeah, we probably could. So if you were to find one of these two sides, you can then use that in a 90-degree angle triangle to find it. I'll only do it one way, okay? But you could look into seeing how you could do it the other. So, how do I find one of these two sides? Well, I have a 16-degree angle opposite that side, and I need one side and the opposite angle there. So we definitely need to include this 40 meters because it's the only side that we know of our non-right angle triangle. The opposite angle to that 40 meters is up here, so we need to figure out what that angle is first of all. Might take one or two steps, depending how you think about it. I'll go that this angle in here is going to be 180 take 22 because they're both on the ground. Angles in a straight line means that we have 158 and 22 makes up the full 180 degrees. So if that's 158 degrees, then 180, take 158, and then take your 16 angles in a triangle will give us that other angle up here, which is the important one because it's opposite the only side of length that we know within this triangle. Should be 6 degrees. So this angle up here, 6 degrees. Diagram's looking a little bit busy. It's unfortunate, but we'll carry on. The length that I'm going to try and find is this one here, which I'm going to label as x. So x on what is the angle opposite the x? That was the 16, which I connected with these two lines. Sine 16. And the 40 is opposite the sine of 6. Rearrange, we get sine of x is equal to sine 16 over sine of 6. This up for you guys. Now, I'm going to leave that the way it is. It's not quite what we need to work out. We still need to work out the height of the sand dune. It is in a right angle triangle, so we don't need to use the sine rule. However, it would work, but sine of 90 is 1, so eventually it's just going to not do a whole lot for us. What we can do is use SOHCAHTOA. Alright, 90-degree angle triangle, opposite and the hypotenuse, not the adjacent. Okay, so sine of 22 degrees is its opposite side, h over x, which we found a value for, but I'm going to keep it as x for a moment. So h is equal to x sine 22, but we know x is 40 sine of 16 over sine of 6. Multiplying that by sine of 22. So substituting what we had or found already with into this height equation. And once we type this into our calculator, we should have our answer. So 40 times sine of 16 times sine of, careful, let's do divided by sine of 6. And I feel safer typing that in as times sine of 22. You might prefer to use the fraction button on your calculator. I feel like that would have been a little bit easier for me at this stage. But carry on. Fraction looks good to me where I've typed it into the calculator, so that's useful. Same thing, we get height is equal to 39.5 meters, because that's what we're working in. Okay, so we didn't actually work out what x was along the way. That was because we didn't want to introduce a rounding error halfway through. So if you can carry through the answer in your calculator, that's going to net you a more accurate answer. Anyways, that's the end of our examples. Hope that helps, and we'll see you next time.